Alrighty, good morning everybody. Welcome back to Calc 1. Plan for today is we're going to start Standard 9, talking about transcendental derivatives, by which I mean derivatives of trig exponential and log functions. Got my usual office hours of the next few days, today and Wednesday at 11 and at 2, tomorrow at 11 and at 1. And as far as homework goes, on Wednesday we will finally have our Standard 8 quiz. And I also posted a web work assignment, homework 11, which will be due on Friday. So, to business, the exam. Just passed back the first exam. I'm not going to talk about any individual questions in class because not everybody has taken the exam quite yet. But if you want to talk to me about, why I graded something a certain way, why you weren't sure about like a particular problem, I'd be happy to meet with you in office hours or answer any questions you might have over email. Once everybody's done taking the exam, I will post solutions on Canvas in the same place I've been posting quiz solutions. So you can kind of see how I had intended for each of the problems to be solved. And here's what I want you to think about this exam. This is not like an exam in a traditional class where if you totally tanked this exam, maybe you only got one mastery or none or two. That doesn't mean you're going to be failing this class. That does not even necessarily see that as a comforting thought. Just because you didn't do well on this exam doesn't really mean anything for your overall grade as far as the mastery-based system is concerned. If you feel like this exam didn't go as well for you as you would like, be happy to meet with you to kind of talk a little bit about maybe what your strategy was, what you can do differently next time, etc. Happy to keep, of course, doing one retest a week. And also keep in mind that we have 2 more midterms in a final. And each of those exams is going to be cumulative, meaning it'll have questions on there from every standard, including the ones you just got tested over. So standards 1 through 8 are appearing on 3 more exams, so lots more opportunities to earn those masteries, even just from exams. Yeah, if you feel like this exam didn't go as well as you want, I purposely wrote it to be what I considered a hard exam. I'd be happy to meet with you. And you're probably not as bad off as you think. And if you feel like you did really well on the exam, well, good for you. Don't get cocky. Any questions or comments about the exam? Just general questions. Okay. And as I said, I'd be happy to talk outside of class about any problem-specific questions you have. Okay. Oh, this one. Apologize for any politics majors out in the room. A cannibal is buying brains for dinner one day. Goes to the butcher shop, and the cannibal's told that mathematician brain costs $1 a pound, engineer brain costs $2 a pound, and politician brain costs $10 a pound. Cannibal's bewildered. Asks the butcher, why does politician brain cost 10 times as much as mathematician brain? Is the quality that much better? The butcher replies, no, of course not. It just takes a lot more politicians to make up that 1 pound. Okay, as promised, standard 9, so I'm going to go and pass out the packet for that. Okay, so we're finally here and ready to talk about things that separate 120 from 112. And that we are going to be doing our trig exponential and log function derivatives. I know this is probably going to be a scary one for some of you, so we're also going to do some review of each of these types of functions along the way. I'm not just going to assume you remember everything about how cosine or log, natural log of x work. This is kind of going to be our last standard that's designed around how do we differentiate stuff. Once we get through standard 9, there's not going to be any more derivative taking rules or anything like that for the rest of the class. You'll be ready to differentiate everything we will come across for the rest of the semester. And then after this standard, our focus is going to shift less on, it's going to be less on how do we differentiate something and more on what can we do with taking derivatives? Like, what do derivatives tell us about functions? How do derivatives help us solve real-world problems? Those sorts of things. So to start with, we would start with everyone's favorite, sine and cosine. So if you want, back page of this packet is sort of a trig sheet with a copy of the unit circle and some derivative and some trig properties, some of which we are going to be using in this class. So if you want, you are welcome to rip it off. So let's take a look at the function at the unit circle. So, unit circle is just the set of all points whose distance from the origin is equal to 1. It's a circle, radius 1, about the origin. And the idea behind when we want to take sine or cosine of some value is starting on the positive x-axis. If we had some angle, like say 45 degrees or pi over 4 radians, as the case may be, 2 pi radians gives us a full circle. So pi radians is going to be 180 degrees. In this class, we're only going to be using radians. I might mention degrees from time to time, but the functions that we work with are going to, in order for our derivative formulas and stuff to hold, you're going to have to get used to thinking in radians. If that's not your cup of tea, my apologies, but you are incorrect and should change your favorite tea brand. That was random. So the idea is, if you wanted to say take something like pi over 4 radians, we would say, well, pi is half of a circle, so pi over 4 would be an eighth of a circle. And so if this angle corresponds to pi over 4 radians, we would go, if you wanted to say what's sine of pi over 4, or what is cosine of pi over 4, we would go to the corresponding point on the unit circle, so say like this point, and whose angle from the positive x-axis is pi over 4 radians, and then cosine of pi over 4 is going to be the x-coordinate of that point. Sine of pi over 4 is going to be the y-coordinate of that point. So in the case of pi over 4, cosine and sine will actually come out to the exact same number, because this point is has the same x and y coordinate. Anybody tell me, using that copy of the unit circle, what is sine slash cosine of pi over 4 when you come out to? Yeah?
Square root of 2 over 2.
Square root of 2 over 2. So for pi over 4, maybe that wasn't the best example for me to choose, comes out to the same thing. But in general, if you have your unit circle and you want to find what sine or cosine of some angle is, you just go to that point corresponding to that angle, where that angle is between the positive x-axis and and just going above the positive x-axis. You plug in, you look at the x and y coordinates of that point, and the x coordinate will be cosine, y coordinate is going to be sine. So we get a few properties right away from just looking at this unit circle. First of all, we're going to see that if we were to take sine of x and sine of some number, let's say x plus 2 pi, what's going to be the relationship between these two values?
They're going to land on the same point of the unit circle.
Why is that?
Because the second one is a full rotation plus whatever the value of x is.
Yeah. If we were to start at some point x, like pi over 4, and then we were to add, and then if we were to add, say, 2 pi to that, that would be saying, all right, we're going to go starting at 1 comma 0. We're going to go pi over 4 radians, and then we'll go an additional 2 pi radians, meaning a full rotation. We're going to land that back at the exact same point as we would if we had just gone pi over 4 and then stopped, as opposed to pi over 4 plus a full rotation. Also, if we were to do minus 2 pi, we would go a clockwise full rotation, and that would also get us back to the same point. So as Wen pointed out, sine of x and sine, and also cosine for that matter, are always going to be the same if you translate your point by 2 pi, some integer multiple of 2 pi radians. Just corresponding to the fact that if you go an additional 2 pi, that's a full circle, which doesn't have any net effect on the point where you end up. So from this, we can actually say that sine of x and cosine of x are periodic with a period of 2 pi, meaning every 2 pi units, the function starts repeating itself. It takes on the same values every 2 pi units apart from each other. Something else we can sort of see from just looking at the unit circle is this fun little formula. Sine squared x plus cosine squared x. No matter what our x is, no matter what angle we plug in for x, it's always going to come out to 1. Why is that? If we think about sine of x and cosine and sine as being x and y coordinates of a point on the unit circle, why should those values have to satisfy this equation? Rachel?
Because the equation of the circle is x squared plus y squared equals 1.
Yeah, exactly. So this equation right here, sine squared x plus cosine squared x equals 1, comes from the fact that every point on the unit circle has to, by definition, satisfy that its x coordinate squared plus its y coordinate squared is always going to come out to 1. And so, since sine of x and cosine of x are always going to be a point on the unit circle, specifically the point you would get if you started at 1, 0, and you go x radians counterclockwise around the unit circle, and you're always going to end up at a point on the unit circle. And as a point on its unit circle, its x coordinate squared plus its y coordinate squared, or cosine squared x plus sine squared x, in other words, should always come out to be 1. And that's what's going to be helpful for us. It's going to be kind of a nice property for us to work with. If you look at the back of the unit circle, there's a bunch more properties about sine and cosine that you can do with trig. I'm not going to go I'm not going to go through and derive every single one of these formulas because we're not going to use most of them honestly, and I don't know. Actually, deriving these are kind of tedious, if you ask me. But I think these two are kind of getting like the most important properties of sine and cosine. That they're periodic, of period 2 pi, meaning they repeat themselves every 2 pi units. And sine squared plus cosine squared always gives us 1. Little Pythagorean identity in play. Any questions or comments? So let's take a look at sine of x and cosine of x individually as functions of x. And start with sine of x. So sine and cosine have interesting things that happen every pi over 2 units. So let's say pi over 2, something's going to happen. At pi, something's going to happen. At 3 pi over 2, something's going to happen. At 2 pi, something's going to happen, etc., etc. To start with, what are we going to get if we were to take sine of 0? If we were to just plug in 0 for x, meaning we're going to travel 0 radians counterclockwise from this point, and ask what's going to be the y coordinate of this point. Well, 0. It's going to give us 0, because this point is 1 comma 0. So its x coordinate will be cosine of 0 radians. Its y coordinate will be sine of 0 radians. And since sine is looking at the y coordinate, it's going to start us off at 0. Then, as x goes to pi over 2, we go to pi over 2 radians. We're going to go a quarter circle and get to the point 0, comma 1. What is sine of pi over 2 going to be? We're going to take the y coordinate of this point up here. Oh, you're being quiet today. I'm trying to give you a few softballs. Well,
I'll do 1.
that's going to give us 1. Yeah, because the y coordinate, because if you go pi over 2 radians, check out the point you get, the y coordinate is 1 at the top of the unit circle. Dr. Gerstle, isn't pi over 2 bigger than 1? Why is your graph not to scale? Shut up. I'm trying to fit it on the board, and then we're going to do cosine over here so we can see them side to side. And the scaling's a little off, but it'll be enough to kind of see the interesting properties of the function. Okay, so if we go to pi radians, our y coordinate is going to take us down. Our angles are going to take us down to this point over here at -1, comma 0. What is sine of pi going to be? Josh?
It's going to be 0 again.
It's going to be 0 again, because we get a y coordinate of 0. So we're going to go down to here. Sine of 3 pi over 2 is going to take us down to this point at 0, -1. Because 3 pi over 2 gets us 3/4 of the way to a full circle, a full 2 pi. So what is sine of 3 pi over 2 going to be? Yeah, it's going to come out to -1, the y coordinate of this point. And finally, Our last point before it starts repeating itself is going to be going a full circle all the way back to 2 pi. Whose y coordinate is going to give us 0 again. And if we were to go in the opposite direction, say to negative pi over 2, will take us to negative 1. And if we wanted to find, say, sine of negative pi over 2, instead of going pi over 2 counterclockwise, we would go pi over 2 clockwise instead. So say, this would give us our negative pi over 2 angle, which would end us back up at negative 1. And then at negative pi, it'll be 0. At negative 3 pi over 2, it'll get us to 1. At negative 2 pi, it'll take us to 0, and so on, giving us this lovely looking graph for sine of x. So you kind of see this fact that sine of x is periodic with a period of 2 pi. You can sort of see looking at our graph from the fact that if we increase our x coordinate by 2 pi units, from say negative 3 pi over 2 to pi over 2, from negative pi to pi, from negative pi over 2 to 3 pi over 2, we're always going to get the same y values out from our sine function every 2 pi units. So the function is going to keep repeating itself forever, going through these oscillations as we go from left to right. So here's a more calculus-y sort of question. Are there any points where this function is not continuous? Meaning, if we were to look at the graph of this function, are there going to be any points, any values of x where sine of x is undefined, where the limit does not exist, or where sine of x and the limit both exist but are not equal to each other? Yeah?
No.
No, doesn't look like it? Scott?
I was going to say no as well.
Rachel? Sorry, you look like you had your hand up.
I think no also.
I would agree. This thing is going to be continuous everywhere. As far as continuity is concerned, sine of x is actually pretty nice. At any value of x, the function will be defined, and the limit will be defined, and those two values will always be equal. So while we're on the subject, we can also look at cosine of x, which is the same basic process as what we just did, except we're going to take the x coordinates of each point rather than the y coordinates. So, starting out at x equals 0, meaning we're starting off at 1 and 0. We haven't traveled any radians around the unit circle. What is cosine of 0 going to be? Yeah, this time we're using the x coordinate instead of our y coordinate, and our x coordinate of that point is going to be up here at positive 1. As we go over to pi over 2, we get to the top of the unit circle again. What's cosine of pi over 2? It's going to be zilch. 0. And then we could basically keep going in the same way. We went out to x equals pi, we would get negative 1. At 3 pi over 2, we'll get 0. At 2 pi, we'll get to 1. And we'll get the same sort of graph as we would going the other direction. Same basic idea. Our graph is kind of oscillating back and forth between y equals 1 and y equals negative 1. It's just offset by a little bit. So instead of at x equals 0, we're starting at 0 in the case of sine. We'll start at 1 in the case of cosine. Let's get the class involved in a vote this time. By a show of thumbs, thumbs up is going to mean continuous everywhere. Thumbs down is going to mean not continuous everywhere. On the count of 5, I want everybody to give me a thumb for whether you think this function is continuous everywhere or not continuous everywhere. 1, 2, 5. Oh, good. You're thrown off by me skipping 3 and 4. Cosine's like sine in that it's going to be nice everywhere it's defined. It's going to be kind of nice in the sense of continuity and limits, how those work. Any questions or comments so far? It's a little bit weird that if you're traveling in sort of the positive direction of cosine and sine, you're thinking about going counterclockwise on the unit circle, whereas going clockwise is kind of what you would think of having negative, plugging in negative values into sine and cosine. You're used to thinking about, might be used to thinking about positive movement around a circle as being clockwise, you know, like a clock. Math, that is not the case. I remember when I was in grad school, this horribly confused one of my professors who thought instead of being clockwise and counterclockwise, it should be counterclockwise and anti-counterclockwise. Where anti-counterclockwise is like, oh, well, the negative sounding one should be the one that's going in this direction. So, that clockwise, why don't we just call that anti-counterclockwise? Good times. This is a class, by the way, that Dr. Gabler was my TA for back in the day. So, sine and cosine. Kind of comes down to playing around and going in rotations around this unit circle, and there are these functions that repeat themselves every 2 pi units. Sine squared plus cosine squared gives us 1, and other such things. So before I get off the front page of the packet, I want to talk briefly about a quick theorem here. It's going to say that if we were to take a limit as x goes to 0, so sine of x divided by x, it's going to come out to 1. And if we were to take a limit as x approaches 0 of cosine of x minus 1 divided by x, we're going to come out to 0. Could we have evaluated this top limit by just plugging in x equals 0 in the top and bottom? Avery?
No, because it's undefined because UP is divided by 0.
Yeah, if we tried to plug in x equals 0 in the top and bottom, we get sine of 0, which is 0 divided by 0, and 0 over 0 is no good. Similarly, with this bottom one, if we tried to plug in 0 for x into the top and bottom, we would get cosine of 0 minus 1, which is 1 minus 1, or 0 in our numerator, and another 0 in our denominator, and 0 over 0 is scary stuff. I'm not going to prove these theorems. You can prove these theorems using some complex right triangle, SOHCAHTOA magic. We're only going to need to use these very briefly, and then we're not really going to care about them anymore. So, but we will need them for what's going to come on the next page. Speaking of which, The time has come. Let's talk about how we can differentiate our sine function and our cosine function. Because as you all told me, sine and cosine are kind of nice, smooth functions. They're continuous everywhere. They should probably be differentiable. Let's see if we can find a formula for the derivatives of sine and cosine. I know some of you who've taken calculus before are itching to tell me that the derivative of one is the other, and almost vice versa. But we're going to prove it in this class. To start with, let's look at the derivative of sine of x. Howdy. So if we want to differentiate the sine function, do we have any derivative rule so far that will tell us how to differentiate sine of x nicely? Yeah?
Do the quotient rule?
Ooh, quotient rule. Okay, how do you want to do quotient rule?
Well, you just treat it like it's just a normal fraction, so it'd be low d high minus high d low, all squared.
Okay, what's our low and what's our high here?
Our low is cosine and our high is sine.
Whoa, sounds like you're going right for the tangent of x.
Wait, oh, I'm looking at something completely
I was
different.
gonna say, I think you skipped ahead of page.
Oh,
I think-
sorry about
No worries. Once we know what sine and cosine are, then yeah, I think differentiating the tangent function, the quotient rule will help us out. But I think we need to know what the derivatives of sine and cosine individually are before we can do that. Let's see, can we use the power rule on this? Not really, I don't see any exponents. Can we use the product and quotient rules? Don't think so, because not really taking the product or quotient of anything here. Can we use the chain rule? We don't really have multiple expressions going on. We're just doing a single thing, which is taking sine, so don't think we can use those. Don't even get me started on implicit differentiation. I think this one we don't have any nice shortcut methods for differentiating yet. So we're going to go to everyone's favorite. The limit definition. Sine of x plus h minus sine of x all over h. I think I counted 3 groans I heard from the audience. Don't worry, we're going to do this once, and then I'm never going to make you do this again. But I just want you to see where does this formula come from for what we're going to get. So, limit definition of the derivative works for everything. It's usually not the nicest way to differentiate hardly any function, but it does have an advantage over the power rule, quotient rule, etc., in that you don't need to be looking at a specific type of function in order to use the limit definition of the derivative. You can just use it on anything, theoretically. It might not be easy to use it on, but it's very generalizable. So what do you think? We take this sine of x plus h term and write it as sine of x plus sine of h. I see you shaking your head.
No, you can't.
Unfortunately, we can't. If we look at the very back page of the packet, where I give you a list of derivative taking rules, we have a sum formula for sine of the sum of 2 things, and unfortunately, it is not that simple. But we can use our sum formula for the sine function to write out sine of x plus h as being sine of the first term, so x, cosine of the second term, so sine of x cosine of h, plus cosine of x sine of h. And then minus sine of x. So here, I just use the sum formula to expand to write out sine of x plus h as an expression involving just sines and cosines of x and h individually. By the way, let's go back up here for a second. Something I forgot to ask. Let's see. Danielle, can we just plug in 0 for h in the top and bottom?
No.
Why not?
Then you're divided by 0.
We'd be dividing by 0, so we can't do that one by just plugging in h equals 0. So, couldn't do it the easy way, have to do it the scary way. All right, I'm about to do some algebraic magic on this limit. So what I'm going to do is I'm going to combine these two terms, sine of x, cosine of h, and the minus sine of x, and factor out a sine of x, get sine of x times cosine of h minus 1, and then a plus cosine of x sine of h term. And we're going to divide all that by h. So we'll get sine of x times the quantity cosine of h minus 1, and then that plus cosine of x sine of h. If we distributed this out, we would get sine of x cosine of h, and then a minus sine of x term, so this is equal to the line before. Why did I do this? Because you know how back in standard 4 we talked about how we can add or subtract fractions that have the same denominator? Something like a over b plus c over b equals a plus c over b. We're going to do the same thing here, except in reverse. I don't know why I felt the need to spin in a circle as I said that for dramatic effect. We're going to take this big fraction and split it up into two smaller fractions. And we're going to get a limit as h goes to 0 of sine of x times cosine of h minus 1 all over h, plus a limit as h goes to 0 of cosine of x sine of h all over h. So basically, I took this big fraction and I split it up into two separate fractions that if we were to try and combine together, we could just add their numerators since they have the same denominator to them. Yes, Rachel.
Why does the limit as h goes to 0 also?
Ooh, why do we now have two separate limits instead of just a single limit? Good question. And that's because in general, limits break up nicely over sums. So in other words, I'm trying to save myself a little bit of work by skipping a line. But basically what I'm doing is, I'm doing something like this. I'm using the fact that if we were to take some limit as h goes to 0 of some involving two different functions, that's always just going to be equal to the limit of the first plus the limit of the second. Something that we never maybe explicitly said, but that you all are using quite a bit back in standard 2, which is if you want to take a limit of some sum of two expressions, you just take the limit of each piece individually. This property, by the way, is what gives us the sum rule for taking derivatives. The derivative of a sum is the sum of the derivatives and all that. That actually comes as a result of this property here involving limits. All right. Here comes the sneaky part. True or false? If we had some expression involving h's, some function f of h, and we multiplied by 2 inside of our limit, is it okay to just pull our multiple of 2 outside of our limit? And to say take 2 times the limit instead of the limit of 2 times the function? See some uncertainty. Put it to a vote. Yeah, yes, this is true. No, this is false. 1, 2, 3, vote. This one's interesting. Seeing some thumbs up, some thumbs down, some non-committal thumbs. It turns out this one's actually true. Similar to how the constant multiple rule for derivatives works. You can always pull constant multiples inside and outside limits. So here's another question. This one's going to be a little bit sneakier. Say instead of 2, we had another variable like x thrown into the mix. Where if we're taking a limit as h goes to 0 of x times f of h versus x times the limit as h goes to 0 of f of h. Are these expressions going to have to be equal? Thumbs up for yes, thumbs down for no. 1, 2, 3, vote. Seem to like how your thumb's looking. It's like you're doing some sort of gang sign almost. Let's see. Show me your thumbs again. Ryan, why do you say no?
Because it's a variable instead of a constant.
It's a variable instead of a constant? Yeah. X is no longer just a standard number like 2. However, this one's also true. But Dr. Gerstel, X isn't a constant in here. X is a variable. Actually, I claim that X is a constant in this one circumstance. In what way can we describe X as being a constant in taking this limit? Okay.
You're multiplying f of h by the same thing in the brackets as when it's outside the brackets, so it's like, it's a constant in the sense that you're multiplying the same thing for both sides.
That's true. It's constant in the sense that we're multiplying the same thing by both sides. But let's look at one more equality. This one will actually be false. This one is not going to be true. Well, as it's written, this is true, but these are not equal to each other. H times f of h, limit as h goes to 0, should not be equal to h times limit as h goes to 0 of f of h. What's different, though, in these two scenarios? When?
That your value of x in the first one is dependent on the limit itself, whereas in the second one, value of h is dependent on the limit approaching.
Yeah, I think I agree. So in other words, what it's saying is that as h approaches 0, nothing is going to happen to x. X is a variable that doesn't depend on h at all. X is just going to, if h is going to 0, x is just going to say, yeah, cool story, h. Have a nice day as you go to 0. X isn't going to be changing at all as h approaches 0. Whereas over here, this expression h, as h approaches 0, this h is not going to be constant. It's going to be taken on, well, it's going to be approaching 0. So here, you can't pull the h outside of the limit, but you can pull an x outside of the limit as h goes to 0. Since as h goes to 0, x is going to behave like a constant. It's not going to be changing unless we were to take a limit as x does something. Goes to 0, goes to 27, limit as x tap dances back and forth. Whatever x likes to do. So, moral of the story is, x is a variable here, but I would actually say it's a constant variable, meaning with what's going on inside this limit, x isn't going to be changing. H is, which is why we can't pull h outside of the limit here, but x is behaving like a constant in this scenario, and so it's okay to pull it outside of the limit. Any questions or comments about why that's the case? Okay, Dr. Gerstl, where are you going with this? So where I'm going with this is I'm going to do something similar here, in that we're looking at two separate limits right now. As h goes to 0. So in this first term, what I'm going to say is sine of x, that's a constant. As h goes to 0, sine of x ain't changing. It's going to sit there on a bench, I don't know, enjoying its day. Not changing as h gets close to 0. So what I claim we can do is we can pull it outside of our limit and rewrite that as sine of x times a limit as h goes to 0 of cosine of h minus 1 all over h. Keeping in mind that sine of x is being treated like a constant as h approaches 0, and as a constant multiple, we can pull it outside of our limit. We couldn't pull, say, the h term in the denominator, or cosine of h minus 1, because those are terms that have h's in them. They're changing as h goes to 0. But sine of x, you don't care. It's just going to stay like that. What can we pull up from our second limit here? Limit is h goes to 0 of cosine of x times sine of h over h. Well, is there anything we can pull out in front of the limit?
You can probably pull out cosine of x.
Why is that?
Well, the variable is an h, so it's, in this case, it's just going to be a constant number. So we pull out one.
Yeah, just like how sine of x didn't have any h's in it, so we could pull it out in front as a constant multiple. I think we could do the same thing here with our cosine term, which will give us cosine of x times the limit as h goes to 0 of sine of h over h. So here, just applying this constant multiple rule for limits to pull out sine of x and cosine of x out in front, which we cannot do with sine of h or the 1 over h factors, because they have h's in them. They're changing, but sine of x and cosine of x aren't changing if we're taking a limit as h does something. All right, I think the time has come. What is the limit as h goes to 0 of cosine of h minus 1 over h? What's that? McKinsey?
Theorem.
Why is that?
Because of our theorem.
Oh, gadzooks. Theorem says that limit as x goes to 0 of cosine of x minus 1 over x is 0. So you're saying if we just replace our x's with h's, it should still come out to 0? I concur. Oh, pardon. You need a strangled cat noise. Do that every day. How about limit as h goes to 0 of sine of h over h? Josh?
Wouldn't do just one, it's just like our other theorem.
Hey, it's the other part of that theorem. As x goes to 0, sine of x over x goes to 1. So if h goes to 0, sine of h over h should go to the same thing. And wouldn't you know it? The derivative of sine of x is cosine of x. Oh man, wish I hadn't erased the two functions now, but kind of ran out of board space. Turns out that at any point on the graph of sine of x, like at x equals 0, you want to know what the slope of the sine function looks like at x equals 0? Take cosine of 0 instead, and you'll get 1. So sine of x has a derivative of cosine of x. That, by the way, is why I wanted this theorem, so we could apply these two results here to help us differentiate the sine function. Because otherwise, if we didn't have this result, we would have gotten stuck at this point, I think. Any questions or comments about what we just did? Okay, let's do the same thing for cosine. Now we're going to let, I don't know, g of x be equal to cosine of x. And we'll need to find g prime of x, which will be a limit as h goes to 0 of cosine of x plus h minus cosine of x all over h. But I tell you what, instead of me standing at the board and doing a bunch of algebra, why don't you all try this one out for yourselves? So what I'd like for you to do is take the next couple of minutes and see if you can do a similar process to what we did for sine of x. And I think you'll end up going through a very similar sequence of steps in order to do it. To see if you can find a way to simplify our formula for the derivative of cosine of x. And I'll help get you started here. Something that you might want to end up using is the sum formula from the back page that cosine of x plus h is going to be equal to cosine of x, cosine of h, minus sine of x, sine of h. So using this sum formula and doing some similar stuff to what we did for sine of x, see if you can differentiate cosine of x in a similar sort of way. And you think you have it, or if you're getting stuck, flag me down or talk to a friend, especially if you have it. And we'll reconvene in a couple minutes here to see what you found. Oh, and then on minus. So the additional will kind of combine the sine of cosine. If you multiply that, it's sine of x. Minus the sine of x. Just read. Definitely a lot of terms floating around here to keep track. So Josh, once you know how to differentiate sine and cosine, then you're absolutely right. If we wanted to differentiate tangent, use those in conjunction with the quotient rule to make it happen. Class is gloomy. Probably because we're doing trig functions today. All right, here's what I want to do to alleviate this. Everybody stand up. Want everybody to breathe in, take a nice deep breath in. Spin in a circle. And say, I'm doing all right today.
I'm doing all right today.
Good. Okay, you can sit back down. Y'all need some, yeah, figured y'all needed a little something to break you out of your trig stupor. So, just make sure we have enough time to get through this in the last couple minutes in class. So how can we rewrite our initial limit? We were to split this up, cosine of x plus h minus cosine of x all over h. If we were to rewrite cosine of x plus h using our sum rule for cosines, how could we rewrite this expression? Dara?
Cosine of x cosine of h minus sine of x sine of h. And then minus cosine of x over h.
Still minus that same cosine of x term all over h. Sounds good? Use the sum rule for cosine to split up cosine of x plus h into this expression. Cecilia, where can we go from there? How can we rewrite this further to help us out?
You could do limit as h approaches 0, and then pull out a cosine of x. So you do cosine of x times cosine of h minus 1 over h.
I have a feeling here you're on the next step in what I have in my mind. Okay, so you factored a cosine of x out from the first and third terms, it sounds like.
Mm-hmm.
And then you wanted to split this up into two separate fractions. Okay, I'm on board. So that'll give us a limit as h goes to 0 of cosine of x times cosine of h minus 1 all over h. And what else will we have?
Me, again.
Since you asked, yes.
Okay. Subtracted by the limit as h approaches 0 of sine of x times sine of h over h.
Sounds good to me. Kind of breaking breaking this one big fraction up into two smaller fractions. What step can we take to pull something out of each of these limits in order to give us limits that look more like what's in the theorem? Rachel?
Pull the cosine of x and the sine of x to the outside of the limit.
Why those two terms specifically?
Because they're common.
Yeah, we can pull these outside of our limit because they don't have any h's in them. They're constant with respect to the variable h. Unlike cosine of h minus 1, sine of h, and h, which we couldn't pull out. So that'll give us a cosine of x times limit as h goes to 0 of cosine of h minus 1 over h. Minus sine of x times a limit as h goes to 0 of sine of h over h. And finally, how do we simplify these two limits? Avery?
Well, the cosine of x will go away because the limit of as h approaches 0, cosine h minus 1 over h is 0. And then the sine over x is just sine over x because the limit of h as h approaches 0, sine of h over h is 1.
Like that? So what is our final answer then simplified to, Avery?
Negative sine of x.
Gadzooks. Or dare I say, awesome possum. We differentiated our cosine function, and while we didn't get sine of x back, we did get negative sine of x. So the derivative of sine is cosine. The derivative of cosine is negative sine. And in essence, Dr. Gerstel, are you going to make us memorize that? Yes. You have to memorize that the derivative of sine is cosine, or the derivative of cosine is negative sine. Or alternatively, you don't have to memorize that, but you can go through this every single time you wanted to evaluate your limits. And then Josh, I know you're itching to get to them, but we'll start class up on Wednesday by talking about how we can differentiate our other trig functions. So hope you all had a good rest of your day. I will see you all on Wednesday. Again, if you have any questions about the exam, I'll be happy to talk to you about them outside of class. And once everybody's taken the exam, I will post solutions and let you all know those are up. Have a good day.